welcome to the video. Today we are going to extend further from our series on coin toss probability concepts. Okay, today we are going to cover union and intersections. So whenever I discuss any new concept, I try to make sure that first we visualize what we are learning and then we learn about the formulas, right? Because a formula is very much like directions through a maze. You can follow the directions, but you will never be able to understand the maze if you do not visualize it. Like if I, give an example of a maze. Um, okay, so let's say if I block it here, and then I block it here. Okay. So if you do not know this maze, what will you do? You will simply, you can still follow instructions. You can go from here, you can find here, there's nothing, then you move forward. Maybe you will go here, you will see a stop, and then you move here, and then you can able to still go out. But you have never understood the maze. So let's visualize first what are unions and intersections. So it is very easy to visualize them in terms of Venn diagrams. Okay, so this is one event, this is the other event. Okay, by now I think the event is, are you comfortable with the word event? Event means something that we desire to ask, or it is one of the outcomes out of many outcomes, right? Like a coin toss is a activity and head is an event. So generally we talk about the probability of that event happening. So that is what an event is. So let's say there are two events, A and B. So what is union? Again, you might guess easily that it is all this area, which is here, which is inside, and then which is also inside here. Okay. So this is union with two events. Now let's see what it is for three events. So we have one event, second event, and a third event. This is A, this is B, and this is C. This is the union of A times B times A, B, and C. And it is written as A union B. And this will be written as A union B union C. So as you can see here, this area is an intersection, which is A intersection B. This area here. Similarly, here it is this area. This is A intersection B intersection C. But there are other areas also, like this one, and this one. These are also intersections. So this is A intersection B, this is A intersection C, and this is B intersection C. So this is overlap region. This is expanded area through A and B combined. Okay, and this is overlap. Next, let's see what else we can learn from here. So in two events, you have A here. If I ask you, what is not A? So we already know A. Then what is not A? It is given as, it is shown as AC, complement, A complement. And similarly, there is a B and then there is a not B, which is B complement. So apart from this A, everything outside of this region is A complement. Like this is, I do not want to write A complement because it will also cover B complement. But you can visualize from here that anything which is not A is called A complement. Anything which is not B is called B complement. Similarly here also. So there is a C, and anything which is not C is called C complement. So a probability of A union B is probability of A plus probability of B, which is this circle, minus probability of A intersection B. Why we are subtracting this is because this is because of double counting. Okay, in this case. So probability of A is everything which is inside A. Probability of B is everything inside B. Now this area has been counted twice, so that's why we have to subtract one of it. Okay, then this one, probability of A union B union C is probability of A plus probability of B plus probability of C. So we have counted A, B and C. Now these are counted twice again. All these intersection between the two events. So we have to subtract P of A intersection B, subtract P of B intersection C, and subtract P of C intersection A. So we have subtracted this, we have subtracted this, we have subtracted this. So what we have done, if you think about this center portion, so we counted it in A, counted it in B, and counted it in C. So 3 times we have counted. Now we have subtracted into A and B, then A and C, and then B and C. So 3 times we have already subtracted. So then this is out of the equation. So we have to again add A intersection B intersection C. Okay. So these formulas look heavy on paper, but if you try to understand it, what is happening visually, then this will make a lot of sense. 10 coin tosses. So we have head and tail, head and tail, head and tail. What is the probability of getting at least one head? Okay. So one way that we can start doing this is we say that, okay, so we get one head here and then all these are tails, or we get one head here and all these are others are tails, or we get one head here and all these are others are tails, we get one head here and all of these are tails, we get one head here and all of these are tails, then we get two heads and all of these are tails, we get two heads here, all of these are tails, then we get two heads here and all of these are others are tails, then we do three heads because it's an at least, right? So we do 3, then 4, then 5, then 6, then 7, then 8, then 9, then 10. Okay. So that will take a hell lot of time. Okay. So what do we do instead? We find the complement of what we are saying. What is the possibility that we can have no heads in this? So what is that? What are the number of ways that we can get no heads? There's only one way, where all of these are tails. Right? Okay. So we get 10 tails in only one way. So how many number of total arrangements are there? 2 to the power n, which is 10. So 2 to the power 10. So how many ways are there? Let's say if A is minimum one head in 10 tosses. So what will be A complement is no head in 10 tosses. What is the probability of A complement is 1, that there is only one way where all of them are tails, divided by the total number of A's, which is 2 to the power 10. So what is the probability of A? It will be 1 minus probability of A complement, which is 1 minus 1 by 2 to the power 10, which is 1023 divided by 1024. Okay, so A complement is basically used in this way. Sometimes it is helpful. Now let's see how to calculate the intersection probability, P A intersection B. A lot of times we have to assess this from the question paper itself or from the question itself, but when the events are independent from each other, for independent events, probability of A intersection B is equal to probability of A multiplied by probability of B. Okay, they can still overlap like this. Like that day I was talking about 2 coin tosses, right? Like 2 coin tosses or 1 coin toss plus 1 dice roll. So they are independent of each other. So this is from the first coin toss, this is from the second coin toss. Or this is from the 1 coin toss, this is from 1 dice roll. Okay. So this is important, that they are independent events. Now for mutually exclusive events, probability of A intersection B is 0. So this, it will not look like this. It will look like so let's say if we are given that A is a probability of head in 1 coin toss and B is a probability of tails in 1 coin toss. If we get A, then B will never happen. If we get B, then A will never happen. Okay. So these are mutually exclusive. So at that time, the probability of A union B will become probability of A plus probability of B in those cases, wherever they are mutually exclusive, not independent. Okay. So this one will give us this equation. Okay. So I think so far we have covered most of the concepts in probability. I will see if there are any more pending, but in the next videos, let me bring in some good questions where we will be applying all the concepts that we have learned so far. Okay. Hope you like this video.